So today I'm going to talk to you guys a little bit about how we're harnessing the power of Spark for building data engineering and analytics applications. So I'll introduce myself a little bit and then get into some additional background. So I have about 11 years in the technology consulting industry. I've been with ZS for most of that and been in our India offices, our US offices. So I work, throughout my work has been in data management. And I've seen the change in the data management landscape going from very traditional tool-based systems and applications to the full elastic cloud-based big data solutions and all that. So I've been part of a number of different very large-scale application builds and platform builds. So I'm going to share a bit of the types of things we've learned in our course of going through that. One pulse check in the room, how many of you are developing things on Spark actively or would categorize yourselves as developers as well? Okay. Engineering managers or technical managers? Few. Okay. Perfect. All right. So both sides of the group should have something or the other to take away from here, hopefully. Yeah. All right. So quick introduction about ZS. So we are a professional services firm. We do a lot of different things, but at the heart of it, we are on the business consulting side doing strategy. We are also doing a lot of technology work with our clients, helping them build solutions. So I work within our technology group. So we're about 6,000 people strong. So our technology group itself is about 2,500 people in this. So there's a very sizable technology team that we have. And we do work across the globe. So a lot of our business is in the US, a lot of it is in Europe, some on the Asia Pacific side as well. Much of the use cases I'll talk about today are more US focused because that's where we see a lot of the data volume spikes coming in, and those are the ones that I've been very closely involved with. So let me talk to you guys a little bit about the types of problem statements that we deal with and the solutions that we have built for that, right? So a bunch of our clients come to us and say, hey, we've got a lot of variety of data. My teams don't have access to it. And all the work I'm talking about, by the way, is Fortune 200 clients, so very large-scale enterprises. They've got multiple departments and functions internally. So in some cases, you'll be surprised on how often we get calls from companies that are out there taking analytics solutions to clients. They're selling analytics solutions to their clients, but another function within the same company would approach us and ask us for help in certain cases that would seem very basic. Right? So those types of things do happen. But a lot of times we would get involved with groups that have a variety of data. A lot of it is built in proprietary applications that's stuck there. In some cases, it's in internal databases, FTP files, external vendors, and their teams don't have access to that. So we get into building enterprise data lakes for that. Some others come to us with a request for building scalable, just BI, DW, or traditional stuff, but it's generally they come to us when there is a very significant scale involved, right? There is a new product launch coming in, or there's a new acquisition that they've done, and things like that. So scale of the data is going to change. There are some cases where we also get involved in building specialized analytical applications. These would be complex problems that need visualization solutions and maybe a graph database behind, or other types of advanced solutions where you have to build search applications or things like that. So those are also situations we get involved in. And then there are increasingly more and more cases where data scientist teams or advanced analytics teams are coming in. And what they're looking for is a way to self-service, do collaborative analytics, right? And an example of that would be a team that wants to figure out that, let's say the three of us are going to do an analytics, I should be able to come and get an environment for myself without talking to anybody else. And once I'm done with my experiment, I should be able to destroy that off, right? So the technology, of course, exists. A lot of products also exist around it, but usually it's trying to do the organizational process around it, a little bit of technology build, and enabling that for the clients. But of all of this, the one I'm going to focus on a little bit today is sort of in these two categories. So I'll talk to you guys about one of the solution architectures, how does it look, and in trying to build that, what types of learnings we had. So here's some highlights of the use case that I'll talk to you about. Right? One of our clients had come to us to say, there is a very, very large commercial reporting and analytics solution. This is for a biopharma client. So these guys were dealing with about 0.5 terabyte of data coming in every week. And the types of business rules and processing and data integration work that needs to happen would convert that 0.5 terabyte to about 3 terabyte. So every week we're producing about 3.5 terabytes of data within that system. So it's a very, very large scale system. It's serving field users. There are sales reps on the field. You've got HQ analytics. You've got data scientists. So a variety of different users coming in and interacting with the system. So the main ask that came in was these types of problem statements exist, and solutions for them usually have a turnaround in terms of days. So you would have like a 3-day, 4-day turnaround for that is very standard. Because this is not a case where you generally build an automated system and let it go. You're dealing with a lot of vendor-provided data. So you run into a lot of data quality issues. There's internal systems where you're doing mastering of the data, and you run into issues on that sometimes. And outputs of these systems, by the way, also go and inform the payout for sales reps. So one mistake in that, and the sales rep's going to be very mad. And there are cases where lawsuits get filed and things get very, very messy, right? So data quality, output quality is of utmost importance. But here, one of the challenges the client came to us was to say, I want to do this within 24 hours. We have to do this every week. It's not good if I get my data, let's say on a Sunday every week, and my reports don't even go out until a Thursday. So you're sending very stale data to our people. We want to accelerate that, reduce the turnaround time, and get very recent data in the hands of the field reps. So that meant if you have a 24-hour SLA, you have to have runtimes on the system that are going to be about 12 to 13 hours, not more than that. Because you need to leave some time for making sure the quality of the reports are okay, any other data quality issues, their impacts are assessed, communications are sent out, and you send outputs with that in mind, right? So that was a big challenge, and that is one of the reasons why we turned to Spark, given the type of processing power that it brings along. But about 50 plus data sources, variety of data sources coming in, a lot of different analytics-ready data sets that we had to create along the way. Right? There are about 500 different business rules and KPIs that we have to calculate in that. 2,000 plus users, as I said, 3.5 terabytes of data. Right? Other interesting challenges that came in is the business rules here keep changing. There are a multitude of functional groups. There are a multitude of data vendors. If a data vendor were to change something, your system business rules have to change to account for that. Right? So there are very frequent changes happening here. The input data itself keeps changing. There are competing priorities within user groups. So one group wants a report out, the other group wants a data pack given to their HQ, right? So both do not want to compromise. So if ever you have to, let's say, do a rerun of the system or fix something in the system, you have to do it without affecting the other group, right? So there has to be some level of decoupling within the system itself. Data quality challenges tend to get complex. You'd have a small change in one data source that would, through the integrations, affect maybe 30 outputs, right? So you have to have ways to keep checking for data quality throughout the system. And finally, the people that are using the system end up being highly business and data experts, right? So none of them are technical experts. And many of them want to come and do a lot of advanced analytics stuff. So we had to dumb down some of the deep technical stuff that is needed for running analytics in a efficient manner, right? So that's a little bit about the problem statement and some constraints around it. Let me get into the solution architecture of what we built for these guys, right? So ultimately, this was a Spark-based solution. So all the data ingestion, the data quality, the data processing, rule application, all of that is happening in Spark. But within that, because we had to make sure the system was nimble and fast changing, we had to get a DevOps pipeline done. So I'll speak a little bit to this. Doing this on especially data platforms is pretty challenging. Right? There are many other factors that come into play. So I'll talk a bit about that later on. So we had Airflow as our orchestrator. So Airflow is a technology where you can write your code in Python, and it generates visual DAGs, if you will, the directed acyclic graphs of your workflows. So this was something that our developers, the technical group at least, loved quite a bit, because they're very used to scripting. So you can script your workflows rather than doing a drag and drop in some other tool to make it happen, right? And the Airflow as a technology will take that code script and convert that into a visual representation that the business users or your operations users really like, right? So that was one of the big elements we had introduced. And we had to also do a lot of different small package services within our system, right? So these were repeatable things that you would have, let's say, different workflows do or different pieces of code do. So we took a lot of those, packaged them up, and built them into mini microservices that were hosted in AWS Lambda, serverless code with an API gateway sitting in front of it so that we could control the security from our application, as well as expose that for other groups within the enterprise to start using those types of services. But the interesting part for us was here. So we had actually used Databricks in this solution. So Databricks, the people behind Spark. So our experience, at least using the Spark clusters with those guys, was very, very seamless, right? So We've done a lot of work for clients in Databricks, in Elastic MapReduce in AWS, in Cloudera, in HD Insights and things like that. Across all those tech, at least what we see is if your application is predominantly Spark, you're going to have the best experience with these guys, right? The level of support that they'll bring or the way their services are packaged, it's a very significant difference. Not just for your engineers, by the way, even your analytics users will feel the difference. So this was one of our biggest experiences working with them. It was pretty phenomenal. But the other highlight I'll draw is you'll see a number of different icons here, right? So we had Databricks clusters spinning up and down for every different job. So our use case was, we could have easily spun up one cluster and submitted all the jobs to that and had Databricks do some sort of workload management, scale up and down the clusters and whatnot. What we figured out was there was no benefit for us in trying to even send all the workloads to one cluster. It's all elastic. It's all spinning up and down. So the more we are able to segregate logic in our application, the more number of clusters we could spin up. And we could eliminate any sort of dependencies between the clusters at all. Right? So for heavy users of Spark, at least you would have seen there are issues you can run by using a single cluster for large applications in terms of garbage collection times that some of your jobs might slow down or error out. There are generally competing loads on the cluster itself. So some of your jobs will suddenly start taking longer than needed because there are other jobs running on the cluster and things like that. But with this type of an architecture, so same is true with Elastic MapReduce also, by the way. So there is no incremental cost of spinning up another cluster. So in our case, literally every single ETL workflow that we have in the system runs on a different cluster. Right? The only incremental cost really you're paying is another driver node. Right? There isn't any other cost per se tied to that. So with this, there was a lot of isolation within the application. And the other part that we were able to do was each of the workflows that we are running, we could get a cluster that's tuned to that workflow. Right? So it gave us a lot of flexibility in trying to right size each of our clusters for the jobs that we were trying to run on those. Finally, the outputs of that get stored in S3. So this is the other big thing that we had done was there is 100% decoupling between our storage and compute. Right? There are no cases where the data that we are processing or the output of one cluster that needs to go to the other one gets exchanged within the clusters or any other way. In every case, every single workflow of ours always reads data from S3, writes it back to S3. So in initial versions of applications that we used to do for our clients, we always used to have like a HDFS layer on a cluster, and then we would have Spark go and pick up from HDFS, run through that, and then write it back. But that always created a dependency on us to have the cluster that stored the HDFS scale. Right? So instead of that, now with S3, we store all our data there. It's infinite scaling for the application at least. Right? The other thing that you'll see with groups like Databricks is that they're bringing a lot of accelerators to make this as fast as possible. EMR, so AWS is investing in EMR S3 connectivity to be faster. Databricks guys are also investing in their own connectors. Spark community itself is bringing up different committers on their own. So in general, the effort of reading and writing directly to storages like S3 is going down. Right? So everybody's working towards that. So building applications the right way for us at least is, at this point, is a 100% decoupling. So all our storage lies here. We just spin up things for compute as and when needed, and we shut them down. Right? From an end user perspective, we've got people working with notebooks. So there are Databricks notebooks in this case that people are working with. When we do EMR, we do Zeppelin notebooks that are packaged with an EMR that are accessible to users. We do put data in fast SQL stores like Redshift generally, because that's when we have BI solutions coming up in the ecosystem. BI solutions integrate very well. A lot of clients are comfortable with that. So that ends up being a portion of our solution. And then there are solutions like Athena coming in for serverless querying. Right? This is when we have loaded data, we don't have an analytics-ready data pack for that, and somebody needs to run a query that isn't optimized any other way, so they can come and work through that. Yes, sir?
Would you be using Athena and Redshift for the same client, or is it?
Same client. Yeah. At this point, I think the trend we are seeing in the industry is there are a multitude of consumption tools coming up. Each one has its own pros and cons. That's why the big thing is that if you have data, let's say, sitting in a store like S3, you at most will need to go to each of these places and register your data and create your metadata, your table definitions and things like that. But each of them has their own optimizations to work with it. And with the advancements that are going on with services like AWS Glue, we're at a point almost where you would have a centralized metastore, one place where you go and do your table definitions, and all technologies will talk to that. So those are active things we are working with clients for. But at least as of now, that part isn't as stable yet where I can say that we have done it. We're actively working on that piece. But it's very interesting that you take a Databricks notebook, for example. It lets you run SQLs. It lets you run PySpark, Scala, all of that. Yet some of the business users who are so used to writing SQLs come back and say it's still not as easy for me. And those are cases where, interestingly, they find it much easier to work with these types of technologies, where it's just SQL is the only way you interact with them. Right? So that's why we still have to enable these types of things. They have their own benefits in some of the other cases. But over time, we see a trend where as users get used to the system, they learn more about the data that's available there, they themselves start switching over to notebooks. Right? That is becoming more and more the way to go for analytics at this point. So that's a little bit about our end-to-end flow, right? So the one thing I'll call out here is that the number of clusters that we are spinning up every week tends to be in the range of about 80 to 100. Right? So as I said, every single workflow that we are running is split up on its own cluster. And in the world of Databricks, at least, you can launch a cluster in about 2 to 3 minutes. That's all it takes. EMR, it's still 10 to 15 minutes. Some others would take longer, but here, literally every 2 to 3 minutes, we can spin up a cluster. So every single workflow of ours, separate cluster. So as many workflows that we run that week, those many clusters will spin up. Right. All right. So let me talk through some of the types of challenges that we came through. Not all of these are technical per se. Some of these are things that we learned along the engagement, and then I'm going to dive more into some of the technical challenges and sharing some of the practices that we've come up with. One thing that we run into is that generally when clients come in for solutions like this, the turnaround time that we have with them is very short. Usually there is a business priority coming up, a huge discussion has started off, and people see that also as the opportunity to do a technical transformation. And when that happens, you generally have a business goal that cannot move. Could be a product launch, could be an acquisition, but that's a date that cannot move. So you have very little time to try and make all of this happen. So in our case, one of the other challenges that leads us to is that the number of people who understand Spark or technologies like that in depth are very different from the number of people who understand all the data and the rules that need to go in with it. So there's this big divide that continues to exist, right? So we have more and more techno-functional people coming up, but you still can't find enough of them at all times, right? So one of the big learnings for us is that as we're trying to do that is to try and separate as much of the deep technical work from the domain work, and I'll talk a bit on how we sort of go about that. The other issue that we keep noticing is that in at least large enterprises, a lot of your senior ETL people that still act as the gatekeepers of approving your designs, architectures, and things like that, many of them are still not as comfortable with the scripting world as they should be, right? Or the DevOps world, the CI/CD world, or secure SDLC practices, or relooking at how data models are done in a big data environment or in a Spark optimized environment and things like that, right? So there's still a fair bit of education that needs to happen as you go along some of these types of implementations. Infrastructure ends up being another funny one where people go to the cloud thinking infrastructure is going to be cheap, but in many cases, so it is true that your infrastructure is cheap, but in a lot of cases, especially for large enterprises, you're generally on shared infrastructure. So somebody else is paying for a part of it, and sometimes you don't even know that's happening. So the per unit cost that you are paying versus when you go to the cloud where you own your entire infrastructure, in some cases that becomes a delta, right? And part of it is the way accounting happens within the enterprise. If not all the costs are being passed to the department, you suddenly are dealing with all the costs being passed to you. The other issue that does happen is during development, people don't understand that even if I have a process that runs 8 hours a week in production, during development it's going to run 24 hours. Or 16 hours a day for 5 days a week. So the amount of infrastructure cost that you have to budget during the development exercise, that ends up being a very interesting education activity for people, right? And there are active measures you have to take to control it, so you don't have runaway costs. The last thing is, technologies like Spark are becoming better and better at auto-tuning their own code, right? So Spark has a number of different optimizers inbuilt. The cost-based optimizer, for example, that has come up. It does a lot of things to make your code run better and better, but you still have to do some amount of tuning. And this, in my experience, is make or break in terms of how much costs are you going to incur, what type of application SLAs are you going to hit into. So there are some other practices you have to start building within the team in trying to get this part sorted out. Especially if you're building large ETLs, you still have a variety of different jobs coming in. There are going to be some jobs that will be super heavy, lots of joins, lots of aggregations, and the type of tuning you need there is very different from your general lookups or simple data merges, right? All right, so let me get into some other sort of learnings that we ran into, right? So the first question that comes up is, in Spark, you've got SQL, you've got PySpark, you've got Scala. Which one do you choose? And a lot of people are stuck between Scala and PySpark on which one's better. Actually, our vote is for SQL. Spark SQL is the thing, in our opinion, that helps you bridge the divide between your technical folks and your domain people. Right? SQL is second nature to most of the people who understand data. So you're there. Spark itself is investing a fair bit in bringing optimizations for Spark SQL. There was, in fact, possibly even now, Spark SQL, some pieces will actually run faster than PySpark or Scala. But compared to data frames and data sets, some of the Spark SQL code will run faster. Because there are cases where the cost-based optimizers that Spark has more and more optimizations built in for SQL interpretation. Right? So that's a big thing. A lot of people used to, when we started, for example, we knew that Scala would run the fastest. PySpark would be second, Spark SQL would be a distant third. At this point, it's completely reversed. Right? So Spark SQL, the more of your application you can build in that, the easier. So one, it's portable. Every technology and language that you're dealing with for data processing is going to have SQL. Your people are going to know SQL, so you don't have to make them learn another language just to try and build applications on it. The technology is evolving so that it does the optimizations internally. Right? The second thing is that the other trick that we do here is we ask people to write SQLs for all the business transformation, but we encapsulate it within a PySpark script and run it in our system. So for all the SQL people on our side, all we had to teach them was open a .py file, do a spark.sql, encapsulate your SQL and store it. What that helps us do is that the rest of our application thinks of it as PySpark. So if and when we need to go and tune a particular job and we need to run some PySpark specific pieces, it's very easy for us to do. Right? It is, from a system perspective, from a technical perspective, you're still running PySparks. From a functional perspective, you're doing SQLs. Right? So that's a big, a little trick that helps us do that quite well. And in general, we have, because of all of these coming in, we are ourselves a big Python shop, so PySpark was a natural choice for us. So we end up doing all our internal technical component build in PySpark, right? Python and PySpark combination, and all our functional work happens in Spark SQL, right? So this is one way, at least, that helps us bridge some portion of the divide, where you've got domain people and you've got deep technical people. Another thing I'll introduce, how many of you have heard of Spark Modularized Views? It's a library, SMV. Anybody's heard of that? So it's actually on GitHub. I've got the link for that there. So we sort of came across this in work that we were doing with some of our clients, and it turned out to be very interesting and useful for data management applications particularly. So I'll give you a little bit of glimpse of what it does. Right? So it's an open source library. You can experiment with that yourself. So it has a hierarchy of, an inbuilt hierarchy in which you have to organize your code. So it forces you to be modular. So essentially what it says is you've got data sets that you're creating as outputs from your system. Every single data set has to be encapsulated in a module. Right? So you say, here's my output, here's the code, a set of data frame transformations or things like that that you're doing to produce that output. Right? So you package all of that inside a module. You do have to say, in order to generate this data set, here is all the code that I need. Here are the upstream dependencies for me. And the library is smart enough to go and build all the linkages and tell you what the hierarchy of your entire application is. Right? So it's a way for you to document exactly what it took for you to produce something. Right? Then you bundle all of the multiple modules into what's known as a stage, and all of that gets into an app. The other beauty here is that you can actually come into this library and you have a special command to run it, where you can say, just run this one module for me, or just run this app for me, or run this stage for me. So it's got that debugging element built in. Even from a production perspective, you can just go and ask it to give you 3 data sets, or you can ask it to run the whole app by itself. So it's a pretty powerful module that way. The learning curve isn't that hard on this. Here's a simple example of the types of things you would have to do, right? So without SMV, you might as well just create a table with a Spark SQL maybe. In this case, you will first have to define a class. For the specific module that you're running, you have to go and define a class. And you say, what does it need? So here I'm telling it that there are two data sets called Rx and Px. These are mandatory. They don't have, the logic for how to create those doesn't have to be here. As long as there is another module dedicated to each of those, SMV will go and string those back and produce that data if it hasn't been run. Then essentially you can run multiple data frame objects and say what object do you want to return, and that's a way for you to at least keep your code organized. There are many other little things that they have done that's very smart here. So one is enforced modularization. The next is a bunch of ETL functions that exist. So if you notice here, I have to do a union between these two data sets. I've used what is called as a SMV union. So SMV union is an inbuilt function in the SMV library, where what it does is essentially simulates that even if your data frames have different number of columns, it's able to do the union by itself and get you the universe of columns from both ends. Right? So there are very small things like that, for which built-in functions exist. These are all very, very interesting and useful from an ETL perspective. I'll give you some other examples of those types of functions. So I've got here SMV unpivot. Right? So this is a case where you've got data that's pivoted up. So you've got, let's say, 3 columns, and you need that data pivoted down, pivoted up, all of those. So you can come in and specify which fields do you want to use and use the unpivot function. It will add 2 fields, one that tells you what was the column name, the second that tells you what was the value for that specific entity that you're looking at. There is also another interesting part where you can add decouple rules to any given data set. Right? So you can say, okay, in this module, I want to start. Here are the 2 data sets I depend on. Here are the 5 decouple rules that need to run on that. And for those decouple rules, the classic things that you need to do in an ETL is, this is what I want to check. Here is my tolerance level for how many of such failures can I tolerate before I have to say the data is just bad. This for us is huge, because there are cases when we are dealing with vendor data, and they will give us things like address that's null, zips that are null, right? Those things do happen. And if we were to have a strict rule where every failure is an application failure, we'll never proceed. Every week we see some percentage of errors, right? So we have that ability to add some sort of a tolerance here to say up to this percentage it's okay, right? So these types of small things that exist in this library by itself are pretty powerful. So if you're doing a lot of data management in the Spark world, there's one thing I would highly recommend you try out. So next, I'll talk about some extreme performance tips that we run into. Right? As I said, one of the big things that came to us was super high performance, super high speed. We had to try and do what used to take 3 days on essentially another big data application, crunch it down to a few hours in this side. So one major thing I'll say is just segregating your storage and compute, very, very highly recommended. Right? So you start with that. Trust me, if you do elastic clusters, if you aren't on a static cluster, if you do elastic spinning up and down, you will not want to stage your data on the cluster at all. Once you look at the types of advancements that are coming in the Spark world for trying to interact directly with disconnected storages, people are working on that more and more. So it's a design pattern that will let you spin up as many clusters as you need to get your applications to be as performant as they can be. Second thing to understand is Spark is all in memory, right? Everything works in memory, but data doesn't go to disk only when there is a spillover. Every single shuffle that happens in Spark essentially has a disk read-write. And that is one of the reasons why shuffles in Spark are slow. Right? They're still faster than what happens in the MapReduce world, but every time, like one of my first things when I talk to people about Spark tuning within our team is, how many shuffles do you have in your code that you're trying to run? If there are more than 2 or 3 shuffles, that's where your problem's going to be. Just go and look for minimizing the shuffles, and you will sort half your performance problems right there. Right? So this is one big thing to avoid. So there are other implications in terms of data models as well. So for example, if I have to do a third normal form data model, or even a star schema for that matter in the Spark world, I actually challenge my teams to look at what type of redundancy can I build into my data model so that I don't have to do multiple joins. My analytics users shouldn't have to pick up a fact data set and always join with 2 dimensions to make sense of data. If we know 80% of the use cases are going to do that, I would pre-join all of that and create a wide data set for my users to use. Because when they come in, instead of having to run a join that's going to cause data shuffles, if they're able to pick up one wide data set and start with it, best performance. Right? The same thing goes with your general data models as well. Right? So in the old database world, there were other issues or limitations that made sure that data redundancy is limited. Part of it was storage, but the other part also was, of course, making sure your application always has the right data, right? But if you can build redundancies in terms of data quality checks in your system, more and more checks in your system, it's better for you to do some of these joins upfront, ahead of time, and minimize all the shuffles that your application needs to go through. It's a huge performance booster, right? If you're doing other joins by itself, broadcast joins, if you don't see broadcast joins in your code, that's the first area for you to go look at, right? The performance difference of having a broadcast join versus sort merge join, which is the other type of join in Spark, is just tremendous, right? So unless you're joining two large data sets, every other join, if you have a big and a small, has to be a broadcast join. The cost-based optimizer, this is another feature that by default is not turned on in your Spark clusters. Highly recommend you do that. The cost-based optimizer, we've seen drastic performance improvements coming in, especially for typical ETL jobs where things have become 5x faster in some cases. So you have to turn on the settings for this, and you have to go and analyze all your tables, so the statistics for that exist in your metastore, right? So once you have these two, the performance is super fast. If you're doing UDFs, user-defined functions in your application, do them in Scala. It's super fast there. This is one case where if you build those UDFs in PySpark, which you can, performance will suffer, right? Especially because the UDFs sort of get called for every record in your data, right? It's going to run many, many times over. So with PySpark, this is one place where you'll start seeing a slowdown. Right. So here's another example, sort of harping on the point of having different clusters, but this is one thing that we used to have in our system, where we would have a process and a data quality management module for that, to check our outputs, right? So all of this is now broken down to say, let me run the process here. Let me start an asynchronous job to run my data quality. And I proceed to the next process, and I start the asynchronous job for data quality processing there. When you're faced with tight SLAs, which was the case that we were doing, looking for opportunities like that is super critical, right? So this was another big thing that helped us shave off a couple of hours in our processing time. Right? Here's an example of a Spark view that I love. So when we are trying to, this is an example of how we run data quality checks in our system, right? So when I have a data set and I need to run, let's say, 20 data quality checks on it, a big thing that I look for is Spark doing all the checks in parallel, right? So this is one case where each of these lines represents an entire check that is happening. So what this tells me is that Spark is running all the checks that I've given it completely in parallel. And then finally, just my data is coming together to be delivered to the next row. Right? If you don't see, especially for cases where you know that your code doesn't have interdependencies, this is the type of view you would like to see. Right? I don't want to sit and orchestrate from outside 200 jobs going to the Spark cluster. I want to package all of that code up, give it to Spark, and see that Spark runs all of that in parallel. Right? So this is one way of verifying that your job is actually running optimal. I'm not going to talk about the details of what's in this picture, but the other thing I'll call out is that if you have Spark experts in-house, you have to work with them to look at the types of applications you're dealing with and try and do a codification of the tuning steps they're generally taking. Right? There is still a fair bit of Spark tuning to be done based on volumes that people are dealing with. This is something I'd created for our internal team to just educate people on that. The first step that it has is people would come and say, hey, I have a Spark job that's not running, and I need help on tuning it. My first advice back to them is you have to go cut your data down and get the thing to run at least once. So we know that you're not coming to a Spark tuning expert with your syntactical problems or coding problems, right? Your data issues and all that. First, go make it run. Cut your data down to whatever extent, and once you have it running, then we'll start through a series of different steps to start looking at where the problems could be, right? And usually there is, the second step that I generally ask them to look for is how many shuffles or stages are you seeing in the job? If it is less than 4, then everything else from that point onwards is to look for additional tuning errors. But if it is greater than 4, then we ask them to start splitting up the job so that it's less than 4 stages per job. Because once you have that many shuffles, it's like entropy always increases. In Spark, the more stages you have, performance always degrades. Beyond a certain number of stages, it will just start degrading no matter what you do. Right? So very, very useful to try and codify your for the types of applications you deal in your organization. Here's another example of some tuning that we had done. So this is from a live use case that we had to work with. So what you see here is like two data sets that we are starting with. The first step in that is join, and it expands in volume. The next step, so there is an aggregation logic built in, then there is another join that expands things, another aggregation, another data set that gets read in, and then some other replication work that's happening which expands the data volume significantly, right? So if you have a job with so many joins, aggregations, and all of that built in, generally what we try and look for is each stage, what is happening, and is that fast enough? Like for this case, for example, there is a join. So all I'm looking for is there a broadcast join? If there is a broadcast join, you're healthy. The next obvious thing to look for is how many partitions of data am I dealing with? And in the Spark world, the more partitions you have, the more things are going to run in parallel, especially for things like that. So that's one of the most important things we start looking for, right? Then for cases like this where there is no broadcast, it's a red flag. There is disk spillover happening, another red flag, right? So these are the types of performance tuning challenges that we're trying to look for into the system, right? So if somebody were to follow this guide in our team, they will be able to solve each of these types of problems that we're running with, right? So there's a little bit of diagnosis that we have to teach them, and a bit of the tuning guide that we have to teach them, and put the two together, 80% of problems at least can be solved. The other interesting thing also is when we're dealing with extreme scale, there are also cases where we have to make a number of API calls and deal with other services, right? So we had cases where, let's say, we were given a whole bunch of customer records, and if we did not find it in our master system, we had API calls to make and check if there was data about that customer available somewhere else. Now the challenge was, in some cases we would only find a handful of customers that needed that scan. In some cases it would be 1,000 customers, 2,000 customers. So now we are dealing with a large number of API calls to be made. Now Spark is a general purpose distributed computing language. It doesn't have to do data crunching. This is a case where we actually put a Python UDF which said, hey, for every data row, go and make this API call. And there are ways in Spark to create a data frame, go to the RDD version of that, and call a mapper. And in that mapper, you give that function. Essentially what it does is this input data goes into the RDD, it creates a map, and it runs whatever UDF you have given for every single record in your data set. And for each record, essentially it's going and making API calls. So if I have a 10-node Spark cluster on which, let's say, I'm running 20 executors or whatever else, each of those executors can go and make API calls on their own. So I'm not limited to a single orchestrator or one single-threaded Python function that's going and making 1,000 API calls. I've essentially packaged all of that up, given it to Spark. Spark distributes, runs that, gets me data back. There's a lot of error handling work that does need to go in when you're dealing with things like that, but this is another extreme performance case where even if you have unpredictable workloads, it might be single-threaded small things that you have to do, but if there is variability in it, you don't know how many of those you got to run, there's another way of distributing all of that so they run faster and you use the power of Spark. The next piece I'll talk about a little bit is DevOps for data platforms. How many of you have built DevOps pipelines for data platforms or data management? So those of you who have built, you'll appreciate the level of complexity that goes into those. But the biggest thing that we sort of keep running into is that when people start talking about DevOps, many of them come from SDLC background where you're building small applications or software products, and it's relatively well-solutioned problem, right? There are many different technologies that exist for it, for targeted things that you have to do. The biggest thing that we keep running into when we're doing DevOps for data platforms is, in this case, the things that can change are my code that introduces problems. It can be the input data itself that I'm running every week that can introduce problems. And in a lot of cases, if you have a large number of business rules, you are going to have some metadata-driven rule executor, right? So I'm not going to code every single rule in my code itself. There are going to be scripts that I will build that will go read off of some configuration table, and that's what's going to apply the rules. So a lot of times your problems can come from the rule metadata, it can come from the input data, or it can come from your code. So how do you test all three things together, right? So that's a very hard problem to solve. So essentially the most important thing that you try and do there is make sure that you create a test environment where your rule metadata and your data, the input data that you're dealing with, doesn't change. And the only variable in there is your code, right? So if you're able to build that, then essentially your test environment at least is insulated. It works to figure out issues in your code. The other challenge then you keep running into is, what if you need to change your business rule because there is an associated change in data? Right, so now your test environment had frozen data which may not have that data nuance that needs to be now tested with the business rule. So there is, every time you run into changes, there is code changes you have to do, there is test case maintenance that you have to do, and there is test data maintenance that you have to do. Right, so that's what adds to the complexity of doing DevOps in data platforms. Right. So, so we have test environments where we have all of that insulated. We also have other test environments where we let the data change, we let the rule metadata change and the code change, and we look for threshold-based testing. Right? So generally from a business perspective, up to a certain percentage change in outputs is okay. So we try and codify things around that. So that at least alarms, so we get alarms if things are changing beyond that. The last thing I'll talk about is a bit on architecting for adaptability, right? So this is one of the other experiences we keep running into. We are dealing with Fortune 200 clients. Many of them, as I said, have other functional departments in there that might be much more advanced in the world of technology than some of the other departments maybe who are coming to us. So as we get into some of these discussions, we find out that there are somebody within the group is already building microservices, and we are expected to integrate with them. We are expected to use them. We start getting challenged very quickly to say, hey, we are architecting microservices, where are your microservices? Right? And that if you have to do an enterprise level solution, you have to integrate with the design patterns that are coming in. So this is where at least 3 patterns that very commonly we see. One is AWS Lambda-based microservices. These are true microservices because more than 15 minutes execution, Lambda will get killed. Docker is being used for running things on Kubernetes or AWS containers for running into ECS. So very common patterns coming up across the board. Right? Many of our clients are already deep into building things like this. Right? So at least the minimum thing that we can do on our part is, if and when we are building small technical components, we try and design them to have an API input signature and an API output signature. The code might just run on whatever Python machine or server that we have going on, but at least codifying it to have API-like input signature and API-like output signature buffers the rest of our application to say, if and when this component were to become a microservice, my solution isn't affected as much. I just have to orchestrate another microservice to get the inputs back. But this is one key thing that we try and imbibe into all the design work that we are doing now, especially on the data management side, because AWS is coming up with so much innovation. Our clients themselves are investing in so much innovation. In some cases, we ourselves are going and helping them build so much stuff that having something like this helps quite a bit. Right? Yeah. All right. So I think those were all the things that I wanted to share with you guys on trying to build some large-scale data management applications using Spark. Thank you so much for making time.